Hello, welcome. In this video, we are going to learn how to find the equation of a line. So let's suppose we have a line. There's our line, and let's suppose this line passes through some coordinates, say A and B. So our goal in this video is to find the equation of this line. What do we mean by equation? We have to find an equation such that if we have an arbitrary point R, say with coordinates x, y, z, we can easily locate the position vector of that point along the line. Alright, so let's begin like this. Since we know the coordinates of A and B, some two coordinates where the line passes, that means we also know the position vectors of A and B. So we actually can find the position vectors very easily. Oops. This should actually be like this. Okay, very close. So let's say the position vector, this is the origin. So the position vector of A, let's call it small a, and the position vector of B, let's call it small b. So our equation of the line should be able to give us the position vector of a point R along the line AB. So let the position vector of R be represented by small r like that. Okay, so the position vector of R, which is, I'll just use OR for the first. So OR, we could take this path, OA plus AR. So there we have OA plus AR. We could also take OB plus BR, but I'll just stick to this one. So as you can see, OR is small r, and OA, that's the vector from the origin to A, the position vector of A, and then AR. So we actually don't know what AR is, but from the properties of parallel lines, I'll just show you this here, that AR is parallel to AB. As you can see, I could say parallel or collinear, so AR is collinear to AB. So what does that mean when AR is collinear to AB? That simply means AR is some constant lambda of AB. Yeah, it could be a half of AB, a third of AB, anything. This is a property of collinear lines when it comes to vectors or parallel lines. So that's very important here. So I'll just substitute for AR in this equation. So I have R equals times AB. But as you can see, AB is actually, I could just say, AB is AO plus OB. Let me do that in a different color. So AB is OA plus OB. As you can see, that is negative A because I'm moving backwards, plus B, that's OB. So that's actually B minus A. So let's write now the equation of the line. Finally, R equals A plus lambda of B minus A. So this is our equation of the line, and you could sometimes find in textbooks we could let B minus A to be equal to something like D. So I just write this as R equals A plus lambda D. Now this equation is very important. It shows us all the useful or the most important components in finding the equation of a line. Number one, we should have the position vector. The position vector of any point. The position vector of any point on the line. We should have the position vector of any point on the line, and then we should also have the parallel vector. So the parallel vector, I also like to call this the directional vector of the line. In other words, you need one point on the line and the direction where the line is heading. So let's see how this is actually used in practice. We'll do this example here. We want to find the vector equation of a line passing through the point A and B as shown here. So let's begin by, sketching this line. Oh, I don't think I need to sketch the line. I'll just carry from the previous derivation that the vector equation is given by A plus lambda D Of course, D is the directional vector. The directional vector. So let's choose this coordinate to be our starting point for the line. All right. I think I need to sketch this actually. So this is the line perhaps, and the line passes through point A. So there is point A with coordinates 1, 3, -2. There is point B there with coordinates 4, -2, -1. So the line passes through point A, and then we also have the direction. It's going from A to B, as you can see. There we have it. So I'll just say the equation of this line is given by OA, which is the position vector of any point on the line, plus lambda. The direction is from A to B. Of course, I could just also say OB plus lambda BA. It doesn't really matter. It still gives us an equation of this line. I'll stick to this one though. So there we have it. OA is the position vector of point A. I could also use OB. No problem there. So OA is actually A minus O. A is 1, 3, -2 minus O is the origin, 0, 0, 0. So that position vector is actually 1, 3, -2. Also, the direction vector, which is AB, I should have put this here. Okay, so AB is actually OB minus OA, where OB and OA are position vectors. Now I'll assume that we have already found the position vectors since they'll actually be the same, but now these are vectors, not coordinates. 4, -2, -1. I subtract 1, 3, -2. So my direction vector or power vector is going to be 3. That's -5. Okay, this is a 3, -5. What's that? Plus, that's a 1. Okay, let me shift this a little bit to this side. Hope you can still see everything. Alright, so finally I could just write my vector equation of the line as OA, which is 1, 3, -2 plus lambda times 3, 5, 1. And there is my vector equation of this line here. As you can see, the most important things we need here is the position vector of any point on the line and the direction which the line is taking. So thanks for watching this video. If you like the video, please give me a thumbs up. Also, share this with others. Subscribe to the channel for more content like this.